NENOMATICA, where mathematics meets YouTube excellence. Welcome to MathGPT. In this video, we'll solve a mathematical problem involving cubic expressions. Let's begin by understanding the problem. Here's our example. We need to calculate the value of a, which equals 1.527 cubed plus 2.47, 3 cubed plus 12 times 1.527 times 2.473. Let's start by substituting some variables to make this problem easier to work with. We'll let it equal 1.527 and b equal 2.473. Now we can rewrite our expression, a as a cubed plus b cubed plus 12 times a times b. Now, let's notice something interesting about our values of a and b. If we calculate a plus b, we get 1.527 plus 2.473, which equals exactly 4. This is very convenient because there's a special algebraic identity for a cubed plus b cubed plus 3 times a times b times the sum of a and b. This expression equals a plus b cubed. Let's look at our original expression again. We have a cubed plus b cubed plus 12ab. We can rewrite 12ab as 3 times 4 times ab. Since a plus b equals 4, this becomes 3 times ab times a plus b. Now, our expression matches the sum of cubes identity that we just saw. Now, we can apply the sum of cubes identity. We have a equals a cubed plus b cubed plus 3ab times a plus b, which equals a plus b cubed. We already calculated that a plus b equals 4. So, a equals 4 cubed. And 4 cubed equals 64. So, our final answer is 64. Let's start by understanding our problem. We are given that x plus 1 over x equals 10, and we need to find x cubed plus 1 over x cubed. To solve this problem, we need to use the cubic binomial expansion formula. This formula states that when we expand the cube of a binomial, such as x plus 1 over x all cubed, we get x cubed plus 3x squared times 1 over x, plus 3x times 1 over x squared, plus 1 over x cubed. We can simplify this to x cubed plus 3x plus 3 over x plus 1 over x cubed. Now, let's rearrange this formula to isolate x cubed plus 1 over x cubed. We get x cubed plus 1 over x cubed equals the cube of x plus 1 over x minus 3 times x plus 1 over x. Since we know that x plus 1 over x equals 10, we can substitute this value. Let's calculate this. 10 cubed is 1,000. 3 times 10 is 30. So x cubed plus 3 times 10 is 30. So x cubed plus 1 over x cubed equals 1,000 minus 30, which is 970. Therefore, x cubed plus 1 over x cubed equals 970. Today, we're going to solve a problem that asks us to compare two mathematical expressions and determine which one is larger. Let's look at our problem. We need to determine which of the following expressions is larger, 2 raised to the power of square root of 10 or 3 squared. To solve this problem, we need to compare these two expressions, 2 raised to the square root of 10 and 3 squared. Let's first evaluate the simpler expression, 3 squared, which is 3 times 3 equal to 9. Now, let's look at 2 raised to the square root of 10. This expression is more complicated, and we can't easily compute its exact value directly. So we'll need to find a way to compare these expressions indirectly. Let's try a different approach. We'll use a comparison strategy. The first step in our solution is to compare 10 and the fraction 361 over 36. We can see that 10 is less than 361 over 36. Let me explain why this comparison helps us. If we can establish relationships between these values, we can use those relationships to compare our original expressions. Now, let's take the square root of both sides of our inequality. Since the square root function is increasing, the inequality direction remains the same. So, square root of 10 is less than square root of 361 over 36. We can simplify the right side. The square root of a fraction is equal to the square root of the numerator divided by the square root of the denominator. So we get square root of 361 divided by square root of 36. Since the square root of 36 is 6, we get square root of 361 divided by 6, which equals 19 over 6. Now that we have established that square root of 10 is less than 19 over 6, let's use this inequality to compare our original expressions. We'll start with the inequality. Square root of 10 is less than 19 over 6. Let's raise 2 to the power of both sides of this inequality. We'll approach this by analyzing the inequality 3 halves raised to the 12th power. We'll compare this expression to powers of 2 and build our way to the final answer through a series of logical steps. Let's start by rewriting our expression. We know that 3 halves to the 12th power can be written as 3 halves to the 4th power, all cubed. This is using the power of a power rule, where we write a as a to the power of m caret n. Why the 4th power? Because 4 times 3 equals 12, so we're breaking down our exponent into smaller parts that will be easier to work with. Now, let's calculate what 3 halves to the 4th power equals. We can compute this step by step. 3 halves squared is 9 over 4, and 9 over 4 squared is 81 over 16. So, our expression becomes 81 over 16, all cubed. To make our calculations easier, let's rewrite 81 over 16 in a different form. Dividing 81 by 16, we get 5 with a remainder of 1. So 81 over 16 equals 5 plus 1/16. This gives us 5 plus 1/16, all cubed. This rewriting step might seem strange at first, but it will make the next step much clearer. Now we need to expand 5 plus 1/16 cubed using the binomial theorem. This gives us 5 cubed plus 3 times 5 squared times 1/16 plus 3 times 5 times 1/16 squared plus 1/16 cubed. Let's compute each term. 5 cubed is 125. 3 times 5 squared times 1/16 is 3 times 25 times 1/16, which equals 75 over 16 or 4 and 11 over 16. The remaining terms are much smaller, so our sum is greater than 125 plus 4, which is 129. Now, let's compare our result to 2 to the 7th power. 2 to the 7th power equals 128. We've shown that 3 halves to the 12th power is greater than 129, which is greater than 128, which equals 2 to the 7th power. So we can conclude that 3 halves to the 12th power is greater than 2 to the 7th power. Let's rewrite our inequality in a different form. 3 halves to the 12th power equals 3 to the 12th power divided by 2 to the 12th power. So our inequality becomes 3 to the 12th power divided by 2 to the 12th power is greater than 2 to the 7th power. Let's multiply both sides of our inequality by 2 to the 12th power. This gives us 3 to the 12th power is greater than 2 to the 19th power. We can see this because 7 plus 12 equals 19. So 2 to the 7th times 2 to the 12th equals 2 to the 19th. Now, our goal is to compare 2 to the square root of 10 with 3 squared. Let's relate this to our current inequality. 3 to the 12th power is greater than 2 to the 19th power. We need to convert our exponents to make a direct comparison. We can show that 2 to the square root of 10 is less than 2 to the 19 over 6 power. This is because the square root of 10 is approximately 3.16, and 19 divided by 6 is approximately 3.17. So we have 2 to the square root of 10 is less than 2 to the 19 over 6 power. Now, we need to relate 2 to the 19 over 6 power with 3 squared. To connect all our inequalities, we need to relate 2 to the 19 over 6 power with 3 squared. Let's work with our inequality 3 to the 12th power is greater than 2 to the 19th power. We can raise both sides to the 1/6 power. 3 to the 12 times 1/6 power is greater than 2 to the 19 times 1/6 power. This simplifies to 3 squared is greater than 2 to the 19 over 6 power. Combining with our previous inequality, we get 2 to the square root of 10 is less than 2 to the 19 over 6 power, which is less than 3 squared. Therefore, by the transitive property of inequalities, 2 to the square root of 10 is less than 3 squared. And that's our answer. Let's recap the key steps we used to solve this problem. First, we wrote 3 halves to the 12th power as 3 halves to the 4th power, all cubed. Then, we computed 3 halves to the 4th power as 81 over 16. We rewrote this as 5 plus 1/16 and expanded using the binomial theorem. This showed us that 3 halves to the 12th power is greater than 2 to the 7th power. We then converted this to show that 3 to the 12th power is greater than 2 to the 19th power. Let's first look at the problem. We are given the cubic equation x cubed minus 18x squared plus 12x minus 24 equals 0. And we need to find the value of the expression x plus 2 divided by x minus 2. To solve this problem, we'll explore a clever approach. We start with the expression x plus 2 divided by x minus 2. Let's see if we can relate this expression to the cubic root of some value. We can write this as x plus 2 divided by x minus 2 equals the cube root of the expression x plus 2 divided by x minus 2 to the power of 3. Now, let's expand the expression in the cube root. When we cube the fraction x plus 2 divided by x minus 2, we get x plus 2 cubed divided by x minus 2 cubed. Let's expand the numerator and denominator. For the numerator, we have x plus 2 cubed, which gives us x cubed plus 6x squared plus 12x plus 8. For the denominator, we have x minus 2 cubed. We have x minus 2 cubed, which gives us x cubed minus 6x squared plus 12x minus 8. Now, let's substitute these expansions back into our equation. We get x plus 2 divided by x minus 2 equals the cube root of the fraction with x cubed plus 6x squared plus 12x plus 8 in the numerator, and x cubed minus 6x squared plus 12x minus 8 in the denominator. Now, here comes the key insight. We know from our original cubic equation that x cubed equals 18x squared minus 12x plus 24. Let's rearrange our original cubic equation to isolate x cubed. Now, we'll substitute this value of x cubed into both the numerator and denominator of our fraction. For the numerator, we get 18x squared minus 12x plus 24 plus 6x squared plus 12x plus 8. Simplifying, we get 18x squared plus 6x squared plus 12x minus 12x plus 24 plus 8, which equals 18x squared plus 6x squared plus 12x minus 12x plus 24 plus 8, which equals 24x squared plus 32. Similarly, for the denominator, we get 18x squared minus 12x plus 24 minus 6x squared plus 12x minus 8. Simplifying, we get 18x squared minus 6x squared minus 12x plus 12x plus 24 minus 8, which equals 12x squared plus 16. Now, let's substitute these simplified expressions back into our equation. We get x plus 2 divided by x minus 2 equals the cube root of the fraction 24x squared plus 32 divided by 12x squared plus 16. We can factor out common terms. Both the numerator and denominator have common factors. The numerator, 24x squared plus 32, can be written as 8 times 3x squared plus 4. The denominator, 12x squared plus 16, can be written as 4 times 3x 4. The denominator, 12x squared plus 16, can be written as 4 times 3x squared plus 4. Now, we can simplify our fraction by canceling the common factor 3x squared plus 4. Our equation becomes x plus 2 divided by x minus 2 equals the cube root of 8 divided by 4, which is the cube root of 2. Taking the cube root, we get x plus 2 divided by x minus 2 equals the cube root of 2. Therefore, the value of the expression x plus 2 divided by x minus 2 is equal to the cube root of 2. This problem demonstrates how we can use the given cubic equation to find the value of a fractional expression without having to solve for the roots of the cubic equation directly. To recap, we expressed our fraction as a cube root, expanded the cube, used our original equation to substitute for x cubed, simplified the resulting expressions, and found that the answer is the cube root of 2. Thank you for watching this video. I hope this explanation helped you understand how to approach these expressions and found that the answer is the cube root of 2. Welcome to this math video, where we'll prove an interesting algebraic identity involving cubes of sums. We will prove that for all real numbers a, b, and c, the cube of their sum, a plus b plus c cubed, equals a cubed plus b cubed plus c cubed plus 3 times the product of a plus b, a plus c, and b plus c. Let's work through this proof step by step. We'll begin our proof by rewriting the left side of the equation. First, we'll rewrite a plus b plus c cubed as the cube of a plus b plus c. This helps us apply the binomial theorem later. Now, we'll apply the binomial cube formula to expand the parenthesis. Remember, for any expressions p and q, we know that p plus q cubed equals p cubed plus 3p squared, q plus 3pq squared plus q cubed. Let's substitute p equals a plus b and q equals c. This gives us a plus b cubed plus 3 times a plus b squared times c plus 3 times a plus b times c squared plus c cubed. Let's further expand this expression. We'll now expand a plus b cubed using the same binomial cube formula. A plus b cubed equals a cubed plus 3, a squared b plus 3, ab squared plus b cubed. We'll also keep the remaining terms as they are for now. Plus 3 times a plus b squared times c, plus 3 times a plus b times c squared, plus c cubed. Let's continue by expanding the remaining terms. For the term 3 times a plus b squared times c, we'll expand a plus b squared as a squared plus 2 ab plus b squared, and then multiply by 3c. Similarly, for the term 3 times a plus b times c squared, we'll expand as 3 times a plus b times c squared. Now our expression becomes a cubed plus 3 a squared b plus 3, ab squared plus b cubed, plus 3c times a squared plus 2, ab plus b squared, plus 3c squared times a plus b plus c cubed. Next, let's distribute and multiply out all terms. Expanding the second line, we get 3c a squared plus 6c ab plus 3cb squared. Expanding the third line, we get 3c squared a plus 3c squared b. Now we have a cubed plus 3 a squared b plus 3, ab squared plus b cubed, plus 3ca squared plus 6c ab plus 3cb squared, plus 3c squared a plus 3c squared b plus c cubed. Now, let's rearrange these terms to group similar ones together. We'll collect all terms with cubes, a cubed plus b cubed plus c cubed. Then we have all the terms with a squared, 3 a squared b plus 3ca squared. Next, all terms with b squared, 3ab squared plus 3cb squared. Then we have the c squared terms, 3c squared a plus 3c squared b. And finally, we have the mixed term, 6cab. Next, we'll factor out common terms from each group. From the second line, we can factor out 3 a squared to get 3 a squared times b plus c. From the third line, we can factor out 3b squared to get 3b squared times a plus c. From the fourth line, we can factor out 3c squared to get 3c squared times a plus b. The mixed term 6c, ab can be rewritten as 6abc. For our final step, we need to recognize an important pattern. Let's focus on the terms besides the cubes. We have 3 a squared times b plus c, plus 3b squared times a plus c, plus 3c squared times a plus b, plus 6abc. With some algebraic manipulation, we can recognize that this equals 3 times the product of a plus b, a plus c, and b plus c. To verify this, we can expand the expression 3 times a plus b times a plus c times b plus c, and confirm it equals all our remaining terms. Therefore, we've proven that a plus b plus c cubed equals a cubed plus b cubed plus c cubed plus 3 times a plus b times a plus c times b plus c. And that completes our proof. We've shown that for all real numbers a, b, and c, the cube of their sum equals the sum of their individual cubes, plus 3 times the product of a plus b, a plus c, and b plus c. This identity is useful in various algebraic manipulations and can help simplify complex expressions involving cubes of sums. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.